This is my third and last video on my alum. So this is looking pretty good. There's still one large crystal and a lot of smaller crystals that you might be able to see, kind of. I'll take a picture of that also and insert it kind of over here. But it looks pretty good. There's some like defects kind of forming now on some of them, which may have happened because I had jostled a little bit while kind of moving things that are up near the alum, and so that could have disturbed it. However, it's evaporated a lot, actually, as you can see from the water level. A lot of water has evaporated, and therefore a lot of the alum has come out of the solution. Yeah, and I think that the temperature has been staying at like a really constant kind of temperature and at a good level of humidity and everything, so that everything is still able to keep evaporating. So for something like this, I obviously have like a ton of little ones again. So it's not just, one big one. However, there's definitely a way to kind of create only one larger crystal. And so to do this, you'd want to basically only allow one to kind of be growing at a time. And so to do that, you could, I guess one way, which would be a little bit more wasteful, is to just remove any other crystal as it's being created. However, if you don't want to do that, you can also tie like a fishing twine or something to it that is very smooth to one crystal, and then kind of suspend it in a saturated solution, and that will allow the equilibrium to occur on all sides of the crystal, which will make it grow bigger and also will not allow other crystals to kind of start growing. So the way we're doing it is kind of allowing multiple crystals to form at the base, which is good to kind of start the crystals to grow. But if you wanted one big one, then you'd have to do something else, because this way all these crystals are kind of running into each other. So this video is going to be more about despacing. So despacing is basically, if you imagine a crystal, it's what's called a lattice. So it's basically groups of repeating atoms. Each kind of repeating chunk is called a unit cell. So you just have like a lot of those stacked next to each other, which will kind of, make the crystal shape. And so if you do that, then you can kind of imagine that each kind of atom is like, if you kind of just chopped it into layers that were one atom thick, and so those kind of just are like separate planes of atoms, then you can say that the distance between those planes is it's basically called despacing. Knowing the despacing can also help us figure out how large each unit cell is, or just the size of like many different aspects of the lattice, without actually being able to see it, because obviously it's so small, it's the atom scale, so we can't actually see it with our own eyes. So we measure despacing by using X-ray analysis. So you shoot X-rays at this crystal, and they will diffract at different kind of amounts, and then that is what you measure. So we can use that graph to identify the different kinds of crystals. We received a graph from our professor about this X-ray diffraction data for our alum. With that, we saw that the lambda we were looking at was 0.15418 nanometers. So the biggest peak was at about 21 degrees on this graph. However, because it's a graph of 2 theta, the actual degrees would be 10.5. So that law says that n times that wavelength is equal to 2 times the despacing times the sine of that angle. So that means that if we want to solve for d, then we can say that d equals n lambda over 2 sine theta. And then we can say that the wavelength, as I said before, is 0.15418 nanometers, and our lambda is 10.5. When you put all that data in, you get the despacing is approximately 0.423 nanometers. Yeah. That's my last video on the alum. I hope you enjoyed it, and thanks for watching.